Welcome to today's paper reading. Today's paper is titled, INDUS, Effective and Efficient Language Models for Scientific Applications. This paper was published on the AR14 preprint by Bishwaranjan, Bhattacharjee and colleagues from IBM Research AI and various NASA centers. The abstract highlights the development of large language models, LLMs, specifically tailored for specialized tasks in various scientific domains. It emphasizes that LLMs trained on domain-focused corpora perform better than those trained on general corpora. The INDUS suite, developed by the authors, includes an encoder model for natural language understanding, a contrastive learning-based model for information retrieval, and smaller models created using knowledge distillation techniques to meet latency or resource constraints. Additionally, the authors introduced 3 new benchmark datasets to facilitate research in these fields. The abstract concludes by stating that the INDUS models outperform both general-purpose and existing domain-specific encoders on new and existing benchmark tasks. The research introduces INDUS, a collection of encoder-based large language models, LLMs, specifically designed for interdisciplinary fields related to Earth, celestial bodies, the Sun, and planets within our solar system. These fields include physics, earth science, astrophysics, heliophysics, planetary sciences, and biology. The development of INDUS addresses the lack of a specific model that encompasses all these fields collectively. INDUS models are trained using meticulously curated corpora from diverse sources, aiming to facilitate research organizations and enterprises by providing efficient access to relevant literature and enabling informed decision-making. Figure 1 provides an overview of the INDUS models, focusing on the general-purpose encoder model and the retriever model derived from it, along with their distilled counterparts designed for efficiency. The figure also highlights the benchmarks used for evaluation, including the new benchmarks NASAQA, Climate Change NER, and NASAIR, which are crucial for assessing the performance of the models in scientific applications. The development of high-quality models requires substantial in-domain corpora. For this purpose, the authors identified and utilized several key data sources. The primary source is the SAO/NASA Astrophysics Data System, ADS, which covers publications in astronomy, astrophysics, physics, and general science. Additionally, PubMed Central, PMC, was used, providing a full-text archive of biomedical and life science literature. The American Meteorological Society, AMS, contributed full-text journal documents on various earth science topics. Further, the American Geophysical Union, AGU, dataset included documents across multiple scientific disciplines. NASA's Common Metadata Repository, CMR, provided text descriptions of earth science data products. To enhance general English learning, English Wikipedia was also included. The total dataset comprises 66.2 billion tokens, processed using Roberta and INDUS tokenizers, with detailed token counts presented in Table 2. Table 1 provides an overview of the basic statistics of the pre-training dataset used in the study. It highlights the total number of tokens, which amounts to 66.2 billion, and breaks down the token distribution across different domains such as earth science and biomedical. The table also specifies the tokenizers used, including INDUS and Roberta. This information is crucial for understanding the composition and scale of the dataset used for pre-training the models. Table 2 presents the number of tokens generated by Roberta and INDUS tokenizers when applied to 1,000 samples from different datasets. The data reveals that INDUS consistently produces fewer tokens compared to Roberta, resulting in an estimated 8% reduction in computation cost during training. This efficiency is crucial for optimizing resource usage and large-scale text processing tasks. The methodology section introduces the INDUS tokenizer, which has a vocabulary size of 50,265 tokens. Out of these, 22,355 tokens are common with the Roberta tokenizer, indicating a significant distributional shift. This tokenizer led to an approximately 8% reduction in computation cost during training. The encoder model, INDUSpace, follows a 12-layer architecture with 125 million parameters and was trained for 500,000 steps using 192v100 GPUs. Additionally, a smaller model, INDUS, with 38 million parameters, was trained using knowledge distillation techniques, employing a 4-layer architecture and also trained for 500,000 steps. Table 3 provides a detailed comparison of tokenization methods between Roberta and the INDUS tokenizer. The key observation is that INDUS tokenizer treats scientific terms, such as biomarkers, phosphorylated, and Alzheimer, as single tokens, whereas Roberta tokenizer splits these words into multiple subword pieces. This difference in tokenization strategy leads to a significant reduction in computation costs during training, approximately 8%, as fewer tokens are produced by INDUS. This efficiency is particularly beneficial for handling scientific texts where specialized terms are prevalent. The methodology section focuses on sentence embedding models, which represent text as low-dimensional vectors to enable efficient use in dense retrieval systems. These models are trained using a contrastive learning objective, which pushes the embeddings of a query closer to relevant passages and further away from non-relevant ones. Inspired by recent work, an improved contrastive loss with an additional bidirectional signal is introduced. The training data includes a large corpus of 300 million samples and employs a stage-wise training approach with large batch sizes and in-batch negatives to better approximate the contrastive learning objective. In this chapter, the authors introduce 3 new datasets to benchmark NLP models in a multidisciplinary domain. The first dataset is Climate Change NER, which includes 534 abstracts annotated with a diverse array of entity types using the IOB tagging scheme. The second dataset is NASAQA, an extractive question-answering task with 145 QA pairs for training and 50 questions for evaluation, augmented with squad data. The third dataset is NASIR, a domain-specific information retrieval benchmark with 498 question-answer pairs, divided into 398 for training and 100 for validation, evaluated using recall at 10. Table 4 presents the statistics and entity labels for the Climate Change NER dataset. This dataset, comprising 534 manually annotated abstracts, is designed to aid in the development and evaluation of NLP models focused on understanding climate-related topics. The abstracts are annotated using the IOB tagging scheme and cover a diverse array of entity types relevant to climate change, such as climate nature, climate greenhouse gases, and climate assets. The dataset is divided into training, validation, and test sets, providing a comprehensive resource for training and testing models in this domain. In this section, we present the experimental results comparing our INDUS models against various baseline models. Specifically, we compared INDUS to RoBRTABASE and SIBERT, and INDUSMAL to MINIM and TinyBERT. Additionally, we evaluated INDUS retriever models against BGE and MINIM v2. The performance metrics used include entity F1 for NER, macro F1 for PICO, and micro F1 for relation extraction. Our models were benchmarked on Blurb for natural language understanding, climate change NER, NASAQA, and information retrieval tasks on NASIR and BIR. The results indicate that INDUS significantly outperforms RoBRTABASE and is competitive with SIBERT. INDUSMAL also shows superior performance compared to TinyBERT and MINIM in most cases. INDUS retriever models notably outperform their baselines in retrieval tasks, demonstrating the effectiveness of our domain-specific models. Table 5 presents the evaluation results on the Blurb benchmark, focusing on natural language understanding tasks in the biomedical domain. The results are averaged over 10 random seeds, with standard deviations provided in parentheses. The micro average is reported across datasets, while the macro average is computed by averaging scores on each task and then averaging these task averages across tasks. INDUS notably outperforms the general-purpose Roberta model on both micro and macro averages, while also achieving competitive performance with the biodomain-specific SIBERT. In smaller models, INDUSMAL significantly outperforms TinyBERT and MINIM, particularly in NER, PICO, relation extraction, and document classification tasks, demonstrating the effectiveness of knowledge distillation from INDUS. Table 6 presents the benchmark results for the climate change NER task. It highlights that INDUS significantly outperforms both Roberta and Siebert, while INDUS shows a large margin of improvement over TinyBert and Minom. The standard deviation over 10 random seeds is provided in parentheses, with results in bold and underline indicating the highest performance and significant difference from the second highest result by more than 2 standard deviations. Table 7 presents the NASAQA benchmark results, showcasing the F1 scores and standard deviations of various models. INDUS achieved the highest F1 score of 68.2, significantly outperforming the second highest result by more than 2 standard deviations. INDUS also demonstrated strong performance with an F1 score of 47.4. Roberta scored 66.8, indicating competitive performance among the models evaluated. Table 8 presents the evaluation results of models on the NASAIR and BIR benchmarks. For NASAIR, the performance is measured by recall at 10, indicating the ability to retrieve relevant documents within the top 10 results. On the BIR benchmark, the average NDCG at 10 is reported, which evaluates the quality of ranked retrieval results across various tasks. Additionally, the table includes the retrieval time per query for the natural questions (NQ) task from BIR, providing insights into the efficiency of the models in terms of query processing speed. In this research, the authors introduced INDUS, a constellation of models specifically designed for the science domain. They showcased the effectiveness of a custom tokenizer and in-domain data in training high-quality encoder models and sentence embedding models. Additionally, they developed smaller versions of these models using state-of-the-art knowledge distillation techniques, making them suitable for applications with latency or resource constraints. For the benefit of the scientific community, the authors plan to release the developed models and benchmark datasets on Hugging Face. Thank you for watching.